At this point, now that we've talked about what parameterizations are, we want to talk about how to use parameterizations to come up with surface areas. So let me just bring this picture back here. What's the surface area of this surface here? If we know our parameterization from the UV land to here, we want a formula that will give us the area, the surface area. And the idea here, I'm not going to go through a complete derivation, but the idea is that if we have our parameterization R of UV is F times I hat plus G times J hat plus H times K hat, where F, G, and H all depend on U and V, we can define partial derivatives of our vector value function here, because this depends on both U and V. So R sub U here would be the partial derivative of F with respect to U times I hat, plus the partial derivative of G with respect to U times J hat, plus the partial derivative of H with respect to U times K hat, and ditto for R sub V. And so the idea here is that we have, let's say that this little region here corresponds to, let's say it's this region right here. The area, let's say the area here is in terms of delta stuff, delta U times delta V. The area over here is going to be, you're going to magnify by a factor of the magnitude, the length of R sub U cross R sub V times delta U delta V. So it's an approximation here because we're using deltas. In the limit, as we take everything to be infinitesimally small, then those will become DUs and DVs and everything would become exact here. But this is the idea. The magnitude of R sub U cross R sub V gives you the scaling factor going from here to here. I'm not going to go through a derivation of that. Take a look at the book. Take a look in the book for more details. So, little definition we need here: parameterized surface R of UV, written out here, is smooth if RU and RV are continuous. Here are the derivatives, remember those. And RU cross RV is never zero on the interior of the parameterization domain. So if we meet all of this stuff, then here's our formula for surface area is going to be, you integrate the magnitude of R sub U cross R sub V dA. This makes sense if you accept me saying that the scaling factor here is the magnitude R sub U cross R sub V, because normally we'd just be integrating 1 here to find area. This, we insert in the factor, the scaling factor here, and this gives us area. For futures, so this is the only thing we need for this section. For future sections, we will often just be thinking about this surface area differential as its own quantity. So file this away for future reference.